Hi guys, I'm Jin Qiu. Today we are going to talk about our recent work, the improving weakly supervised temporal action localization by bridging train test gap in studio level. So let me first briefly introduce about the techniques we used in this work. First, we introduced the module called Gaussian fusion module. This module is kind of use different action boundaries which can be ignored by the NMS procedure. And secondly, with those Gaussian fused action boundaries, we generate snap-wise pseudo label for our weekly action localization problem. Um, Lastly, we use the delta pseudo label mechanism for self-correction of our training process. That is because at the early training stage, the generated pseudo label can be very fluctuating, and this may lead to some errors. And if we have no self-correction mechanisms, these errors will prolong along the training process, and it will cause kind of damage the performance. And now let's get into details of the SS work. Uh, Firstly, oh, what happened? We shall say about what problem we are going to solve in this project. During training stage, we are given n training videos. They are indexed by indexed from 1 to n, and along with those training videos, there are also action categories provided. They are called YI to YM. For each Y, it's actually a vector that indicates the presence or absence of a certain kind of action. Uh, Here, this Y stands for the whole video. It's not snap-wise or frame-wise. So we do not have frame-wise labels uh, in our problem. During testing stage, we are providing with whenever we are providing with a video, our target is to predict a set of action instance. Here by action instance, we mean a tuple that is consisted of C, Q, S, and E. Where C denotes the predicted action class, Q is the confidence score, S and E represents the start time and end time of the action instance. Uh, Previously, there are also many previous works that try to solve this problem. Generally speaking, many relies on the temporal class activation map. It's called TCON for short, and for the TCON are used as pseudo levels. However, as TCON, it differs from the action boundaries needed during our prediction stage, I mean testing stage. So it kind of creates a gap between the training and the testing stage. Also, like currently, the most widely used post processing is kind of like the AMS post processing. Um, AMS is kind of very naive and straightforward. It just throw out any action predictions that overlaps with action with highest confidence above our threshold, and this procedure will kind of introduce many information loss, and it's not sufficient to generate high quality action boundaries. Lastly, we also, as we mentioned before, we also introduced the delta pseudo label to solve the problem that the pseudo label generated at the early training stage can be very fluctuating and inaccurate. Now let's get into details of our training pipeline. Uh, Firstly, we encode our video with an image encoder, and those encoded image videos they are snap-wise TCOMs. So here the TCOMs is snap-wise, and with those TCOMs we use the NMS or not NMS, NMS here. We use those to generate action boundaries, and those generated action boundaries, normally speaking, they are processed by an MMS module. But in our work, we use the Gaussian weighted instance fusion module to fuse those action boundaries. And those fused action boundaries, it has the form that we previously mentioned is the QC and SE form. So it cannot be directly used to train uh, train our action localized module or our action localized model. So we need to generate it back to the snapwise pseudo level. So we use the improved pseudo level generation module. I generated an improved pseudo level snapwise. Uh, then we use this generated pseudo level and use it to minus the previously improved pseudo level to create a data pseudo level. And this data pseudo level is used as the cross entropy loss snapwisely to train our action localization model. For our Gaussian weighted instance fusion, it's very similar to the NMS procedure. We kind of consider the action instances that overlap with the currently most confidence action higher than a threshold and use a Gaussian fusion weight to compute the average of those weighted fusions. Next is the improved pseudo model generation module. For the improved pseudo level generation, we have two assumptions. The first one is the generated pseudo level should preserve the confidence score of each action instance. And the second one is that the score of generated pseudo level should be as uniform as possible. So this leads to the following two constraints. And by solving those two constraints, we can get our improved pseudo level. Here we have a small demonstration of how the improved pseudo level is generated. So the S figure shows that we have four constraints, W0, W1, W2, and W3. And the yellow part, it indicates that there is actions and it's weighted to 1. And the minus 1 is action boundary set to minus 1. And let's distinguish between action and action boundaries. And for those parts that has no action store, is the weight is set to 0. Lastly, we have the data pseudo level part. This is very straightforward. We just use the currently produced input pseudo level to minus the previous one. And now our experiments actually outperforms the previous method by quite a large performance gain. We have like 3.1 or no, not that's the 3.1. Compared to the DLU method, we have like has 2.9 performance gain, and we also studied the influence of the temporal used in Gaussian fusion module and the performance gain of each part. Thank you for your attention.